Okay, so this is for fluid transport. Um, we're going to an introduction to it. This is the original material, this new this material. We wanted to include some animations to make it a little bit more visual, easier for us to visualize what we are looking at. So it's the same content we are using. We are just adding a few animations so that we can see what we are doing. So this is an introduction to fluid. And before we do that, units operations are when we said that unit operations are processes that would involve a physical change to substances. So things like evaporation, drying, crashing, filtration. These are unit operations. And they were originally thought of as separate from each other. So a long time ago, they used to think of these things as separate from each other, that there was no relation between the two operations. And later on, they realized that they were actually related by two things. Okay. Is it better? Is it better? Okay, so they realized that they were actually related by three things. And they were, okay, so these three things were heat, mass, and momentum that was being transferred. Right, so this led to what we call
Hello, could you?
transport.
Yeah, I think your line is breaking a bit.
The line is breaking. I'm coming. Is this one better? Hello. Okay. So this leads to what we call transport phenomena. But when we talk about transport phenomena, we're just considering the movement of a property, be it mass, heat, or momentum, by the molecular movement through a system. So as I said earlier, we just picked a few animations. So these are some of the um, channels we got the animations from. You can visit them for better understanding of the concepts that we are talking about. So when we look at transport phenomena, we see here that we have a hot region and then a cold region. We know that heat will be transferred from the hotter region to the colder region. So this is for heat transfer. We can also have mass transfer, where we have um, a concentration of material at one side, more of a concentration of material at one side. And because there's less material at the other side, we see the material start to move towards the side that has a lower concentration. So this is with the concentration gradients, we see mass being transferred. We also have the momentum transfer. To realize that momentum deals a lot more with forces. Realize that as the white ball moves, it hits the black one and it becomes stationary. So it's transferred its momentum to the other unit. Is that okay? So for heat transfer, we look at hot region to cold region. For mass transfer, we look at a place with a higher concentration to a place with a lower concentration. And for momentum transfer, we look at a place with a higher velocity to a place with a lower velocity, usually. Is that okay? Now, when we talk about momentum transport or fluid mechanics, most of the heat transport and mass transport will be considered in other courses, right? So we have a course, heat transfer, you have separation processes, so you see these things there. So we will be dealing more with momentum transport with this course. But then momentum transport, we can break it into two classes. So we can have fluid statics and we can have fluid dynamics. Just as the names imply, fluid statics, we just consider fluids at rest. Fluid dynamics, we consider fluids that are in motion. So if we look at the first image we have up here, this is a manometer. We realize that after some time, the fluid stop moving and we can pick our readings from there. So we know that for the fluids to be at rest, there have to be some forces that are balanced from the fluids. The study of this is what we can call fluid statics. But then with the image we see down here, we realize that as the fluid, this is air, is moving over the building, it has a particular kind of profile or it has a particular kind of. So studying something like this is what we can call fluid dynamics. It considers fluids that are in motion. Okay. Now we can subdivide fluid mechanics. So we can have hydraulics, aerodynamics, meteorology, hydrology, reservoir mechanics, different kinds of subdivisions of fluid mechanics. But then they all have the same fundamental idea. They are dealing with fluids that are in motion. So if you look at hydraulics, you look at the flow of water in rivers, in pipes. If you look at aerodynamics, you're looking at the flow of air. So around airplanes, around rockets. So these are just some of the subdivisions of fluid mechanics. Please, are we okay? These are just some of the subdivisions of fluid mechanics. Okay. Now, when we are dealing with fluid mechanics, we have two types of equations that we can work with. So the two equations that we consider are balance equations and then phenomenological equations. But we can also call them rate equations. So when we talk about a balance equation or conservation equations, right? These are looking at the conservation of mass, which we call the equation of continuity, conservation of momentum, which we call the equation of motion, and then the conservation of energy, and then conservation of even chemical components, right? So these are balance equations. When we are trying to just balance, it's either mass, momentum, energy, anything of that sort. And these various conservation equations are called the equations of change because they describe the change of density, velocity, temperature, and concentration with respect to time and position in the system. So the general balance equation, which we can specify for mass, heat, and momentum, we have accumulation, which is equal to our generation minus our consumption, our creation minus our destruction, plus our flow in minus our flow out. This is just like what we've seen so far with CPC, trying to get balances for various properties. We also have what we call the phenomenological equations or the rate equations. So these ones describe natural phenomena or natural processes, and they ignore the microscopic structure of a substance. We consider it as a continuous medium. So we'll speak about this, the continuum later on in this particular discussion, so you understand it a bit more. But then these relations consider the microscopic nature of a substance, and we treat it as though it was a continuous medium. So this is able to relate the properties that would define the phenomena that we are considering. So the phenomenological equations are what we call rate driving force equations. We say that they can also be called rate equations, right? And they are necessary for us to be able to write our balance equations. So if we're able to determine our phenomenological equations, we can use them in a way with balance equations as well. Now, the coefficients that we determine for these equations, usually we get them from experimentation. And the way we go about it is we can say that the rate of a transport process is equal to a certain driving force divided by a certain resistance. So the most common equation that we normally use is V is equal to IR, right? So if I make I the subject, I have V over R to be equal to my I. Now, if we are looking at R is the resistance. So we already have that now as a denominator. And we know that voltage, right? We can also call it, in some cases, we can look at it as potential difference. You know that voltage is giving us an idea of a region where we have high flow to low flow. So something that will cause material to flow, or something that will cause current flow. That's what's going to drive the current, right? So we have our driving force here to be the voltage. We are dividing it by our resistance. It gives us the thing that is actually going to flow. So if it was something that was being done considering time or per time, then we can call it the rate of that thing that is flowing. So that's the rate of a transport process. And what we are also saying is that the resistance, so when I say that we have driving force over resistance, we can take 1 over our resistance to be a certain coefficient, right? So that's why down here we see coefficient times driving force. That's all that they are just trying to say. So what we are trying to say from this is that for material to move, there has to be a certain driving force, right? But then that movement can also be retarded or hindered by a certain resistance. So if we have the driving force divided by the resistance, right, considering it's happening in a given amount of time, then we can get the rate of the transport process. Now, the reason why we are speaking about the driving force is this. Realize that when we're looking at mass, heat, and momentum being transferred, talk about the fact that for heat to be transferred, there has to be a temperature gradient. So there has to be a hot region to a cold region. When we are dealing with mass, there has to be a region of higher concentration to a region of lower concentration. So that's given a certain gradient. We have a concentration gradient, we have a temperature gradient, we have a velocity gradient for momentum. The reason why we're speaking about gradients is because realize that if we have a particular gradient, right? Or let me put it this way. For us to have a higher driving force, it means that our gradient has to be steeper, right? And we'll see why we're talking about gradients very soon when we look at the equations. Our gradient has to be steeper. So if we have, for example, let's say this is the slope of a mountain, and we have a water particle moving down along it. We like that to move with a particular kind of speed. And if we have a steeper mountain, right, and we compare the two water particles, realize that the one on the steeper side would move faster. Is that okay? So that's what we are just trying to see, that the gradient is giving an indication of the kind of driving force, what is going to move a material, what is going to transport a material, and it will cause it to move faster if it is higher. That's why the driving force was important. Now let's look at these equations here. You can see the gradients over here. So the first one here is for mass. When we consider mass, this is what we call the concentration gradient, the change of concentration with respect to the change in time. So it's what the change in distance. Right. So if I have a region of higher concentration and a region of lower concentration, mass will be transferred from higher to lower. Then we have that for heat as well. Right. So for heat, we have a region of higher temperature and then the lower temperature region. Heat can be transferred. When we deal with momentum, we have a higher velocity to a lower velocity, and that's how momentum is transferred. So kindly take note of that. The coefficients we have here, right, are like what we saw over here. So a certain coefficient times the driving force. Is that okay? So these are the phenomenological equations that we consider, or these are the things we even consider when we are dealing with transport phenomena. Okay, so what are we trying to say? The balance equations consider the fact that matter, energy, and momentum, they are conserved. We can't create them, we can't destroy them, but they can change from one form to another, like with heat, or they can be transferred, like with momentum. Is that okay? So the rate equations, these are equations that will describe the relation between the movement of the property and the time. So the rate at which heat or mass or force is going to move with time. These are the rate equations. So that's the difference between the balance equations and then the rate equations. Now let's look at fluid properties themselves. When we talk about fluid properties, one of the things that we need to consider is the effect of what we call shear stress. So shear stress is just the shear force per unit area. And we use it to distinguish between fluids and non-fluids. So a shear stress is a stress that is created whenever a tangential force acts on a surface. If you say something is acting tangential, it is acting parallel to the surface we are considering. If we have a normal force and it is acting perpendicular to the surface we are considering. So if you look at the image up here, realize that this is the surface, the brown part, and then the force that is pulling it is acting parallel to that direction. So what we have here is a shear force, right? And that force acting on that area will give us what we call a shear stress. So we can even see the image down here. We have a piece of in between two blocks. When we move the upper block with a force F, right, it would be deformed in this direction. So we are moving it parallel to the direction of the surface. That is the block we are looking at the top here, right? And this is what we call a shear force, introducing a shear stress. So a shear force is just one that is acting tangentially with respect to a surface or parallel to the surface we are considering. Now, when we talk about a fluid, if we are saying a fluid is a substance that can sustain no static shear stress, or as a consequence of the definition, a substance that will deform continuously under any applied shear load. So we see how we are relating, or we understand this definition very soon in the subsequent slides, and we relate the shear stress to the movement of a fluid, or what they are talking over here about the continuous deformation under the applied shear load. So we understand that very soon. And one thing that's saying is that when a fluid is at rest, then it means there is no shear stress. So once again, for shear stresses, they are acting perpendicular to the surface we are considering, or tangentially to the surface. But normal shears, like what we see over here, they are acting, sorry, did I say perpendicular? This one is parallel for shear, and then for normal, it is perpendicular to the surface. So in the first case, it can be perpendicular and it can be pulling the material. So then we call this one tensile. And we have a case where it is now rather pushing the material. So we call that one compressive. Yes. Now, this is where we understand the whole issue of the shear stress thing. We said like fluid is a substance that can sustain no static shear stress, whereas a substance that would deform continuously under any applied shear load. Now, this is what we're trying to say. With this animation at the right here, realize that as the fluid is moving, the one at the lower part is moving quite slowly. The one at the upper part is moving a little bit faster. Now, when the one at the upper part is moving, they are all in layers. So we consider these as three different layers. The one at the upper part is moving parallel to the one in the middle. So it is giving it some kind of force. It is applying some kind of force on it. And as we see here, that is very similar to what we saw when we were looking at what the shear stress was. So as the upper one is moving, it is introducing some kind of shear stress to the middle layer. That's how fluids work. So you realize that this particular block we see here, that is um, giving us the shear diagram, is very, very close to what we saw over here, right? Very, very close to what we saw over here, where it is being deformed in our because we are having a force acting parallel to the surface we are considering. So if we look at this, once again, we have the upper layer that is moving with its higher velocity. It is causing some kind of shearing to be done on the middle layer. So we can see that again. If you just take a certain portion, middle layer, we can see that it is being shared in that direction. And that's how fluids work. Now, when we see that the fluid can sustain static shear stress, what we're saying is that when this is happening, it is going to cause the fluid to deform or to cause the fluid to move, right? And the reason why we are saying that it will deform continuously under any applied shear is because when we apply this, it is going to just continue on moving, unlike with solids. So I think I spoke about that at a point. Okay, so I did. So realize that for with solids, when you apply a shear on them, right, and you use it, it's either it might come back to its original position or it might just stay as it is. You're not going to see the solid flowing. And then with liquids, it's going to continue to flow. That's why I think that they will deform continuously. So for a solid, if I should apply my shear to it, it might end up just like this. If I remove the force, it might either return or it might stay this way. So it has done deforming. But then for the liquid, once I apply this, it is going to continue to deform. It will just continue to flow until there's something that would stop the flow later on. Okay. Now we have two types of fluids. We have liquids and gases. When we consider them on the molecular level, they are quite different. So for liquids, the molecules are close together. They are held together by strong attractive forces. And then with the gases, the molecules are relatively further apart and there are weaker forces of attraction between the gases. So as the temperature and pressure increase, then these differences become less and less. So we have a point where the liquid and then the gas become identical at the critical temperature and pressure. Spoke about this when we're also looking at thermodynamics. Now, the tendency for continuous deformation of a substance is what we call fluidity. So fluidity is the ability for a material to deform continuously. Right. That's why we are, if you look at the term fluidity, it's for fluids. Solids will not deform continuously. Right. And then the act of continuous deformation is called flow. So we say a material is flowing when it is deforming continuously. When a material is deforming continuously, then we say it is flowing. So if we have water maybe on a surface, it is flowing because it is being deformed continuously. It is not staying in the position that it was in. Right? There's some kind of deformation, there's some kind of change in its shape, in the position it was in over time. So it is deforming continuously. But when we consider solids, solids are going to resist deformation by shear stress. So when we remove that shear stress, the solid is going to return to its original size, provided that we need to exceed what we call the elastic limit. Right? So it's either it's going to return to what it was original, or to just stay there. It's not going to happen continuously. As soon as the shear stress is removed, the solid is going to either return to its original position or stay where it is. But for a liquid, it will continue to flow, or for a fluid, it will continue to flow. Right? So for fluids, we are seeing that this is usually not so. That's why we said the fluid is one that can sustain low shear stress, right? But if I dealing with a solid will be able to sustain the shear stress. Is are we okay with this so far? Are we okay with this so far? Hello? Okay. Then that's fine. So we remember I said earlier that we're going to explain what we mean by a continuum. When we're dealing with flow relationships and calculations, we assume that the fluid is a continuum. So what we are saying that is that we can consider that we can divide the fluid without really considering its molecular structure. That's like the individual molecules, right? So this approach is going to avoid the difficulty of dealing with the complexity of molecular motion itself. What we're trying to say by this is that when we look at the individual molecules, it becomes harder to really predict the properties as compared to when we pick maybe a number of the molecules. So if someone is asking that, please doesn't mean fluid in motion is being deformed. Yes, please, it means it's being deformed. Is that okay? When we talk about deformation, what we're saying is that we have the material in a particular shape or a particular dimensions, right? Or yes, with a particular shape in a particular location. If you're saying it is being deformed, then it means that that shape is going to be changed, right? So that's what deformation is constantly. It's a deviation from its original position, its original state, its original structure. Okay. So what we're seeing here is that when we look at the okay, when we look at the individual molecules, sometimes it becomes very hard to predict the properties. So maybe you're looking at the density of your fluid, right? You realize that if you should find the density of the entire fluid, maybe you are getting one particular value or very close to one particular value, right? But then if you are supposed to look at the individual molecules fluid, you realize that the densities will fluctuate because there's a point where it will move closer to other molecules, it will move further away from other molecules and all these kind of things. Right, so when we are dealing with fluid properties, usually we want to assume the fluid is a continuum because if we don't, it becomes harder to predict what we are looking at. But when we talk about a continuum, all we are trying to say is that uh, what we're trying to say is that we can look at water this way, or we can look at water as individual particles. If you look at the individual particles, like each individual particle, it becomes harder to um, work with it. But then if you consider instead of individual particles, we can consider a collection of these particles, right? Then we can easily work with it. So there's a certain volume of material that we can study and we can get very accurate um, results or very predictable results, right? So we are seeing a particle in the continuum is an infinitesimal volume of material. So it's a certain small volume of the material, but we're not considering to get to the individual particles. So now in this case, when we say a fluid particle, we're not actually considering the individual molecules, we are considering a large number of molecules moving together. So that's what we're trying to say by a continuum. So when we say a fluid particle in this point, we're not talking about the individual molecules, but we're talking about a number of molecules moving together so that we can easily predict its properties. Are we fine with this part? Okay. Now we have a few other definitions that we can look at. So when we talk about a field, it is a region. Fair question. Okay, sorry, I'll slow down a bit. But is there any parts you need me to go over? If there's any parts you want to go over, you can just tap it out. I'll just explain it. So we'll talk about a field. A field is a region within which physical or mathematical quantities can be specified or measured at every point. So a field is basically just a region that we are defining, that we are just going to study, or we can observe, or we can define, or we can measure things there, right? And we can specify a field by giving the value of the physical quantity as a function of the independent space coordinates. So we can define our field in terms of a certain length, breadth, and height, right? So maybe I have a certain fluid I'm dealing with a certain fluid. And please, all the things you are saying now, you will need them in the subsequent um, discussion. So it's very important that you really pay attention to these things. Right? You can have a certain fluid, but then instead of considering all of the fluid, we can just take a region of the fluid. Then we can consider it in a three-dimensional plane. So we have maybe the fluid particle somewhere here in this three-dimensional plane. Right. So this now becomes our fluid where we are now going to specify and then measure our quantities. So the fluid is just very, but then remember that every region we can define this by the three coordinate space or the three space coordinates. So length, breadth, and height. Now the quantities of pressure, density, temperature are what we call scalar quantities. So I know we are very familiar with scalar quantities, quantities with magnitude, but then without direction. Right? When we have them being distributed, then we have what we call a scalar field. So we can look at the density distribution of a material, how density is distributed in the material. There's a point where the density is higher, there's a point where the density is lower. When we consider, we call it a scalar field, right? And we can also have vector quantities. So they have magnitude and direction. So things like velocity. When we also consider the distribution of vector quantities in space, then we call that a vector field. So I can look at the velocity distribution. Maybe there's a point where there are higher velocity, there are lower velocities, velocities pointing in different directions. When I consider that region, it becomes what we call a vector field. Now, the properties of a given point in the field can also be functions of time, right? So we can have the property as a function of time. Okay. Now, a flow field is any region in space where a fluid flow exists. So we can have a field and we might have a static material there. The material is in, there's no flow there. Or we can have a field and we can have fluid flowing through that field. So when we have fluid flowing in the field, then we call that a flow field. Okay. Now, this part is a bit interesting. We have different kinds of flow. So we have uniform, non-uniform, steady, and then unsteady. So when we did CPC and we did thermodynamics, we spoke a lot about steady state flow and then unsteady flow, right? So please, let's really pay attention so that we don't confuse these ones with uniform and then non-uniform flow. When we say a flow is uniform, all we are saying is that the velocity or any property we are looking at, right, at any given point is the same in magnitude and direction at every point. So this is what we are trying to say. I can have a pipe. Okay, I can have a certain pipe, right? And then maybe at the inlet, the velocity is maybe 2 meters per second. In the middle, the velocity is 2 meters per second. At the end, the velocity is 2 meters per second. This is what we call a uniform flow. The property is the same at every single point, right? But if at an instant the velocity changes from point to point, and the flow is called non-uniform. So maybe we started with 3, we went to 2, and then we ended at 1. When we have something that is non-uniform, so the property is changing from point to point. Okay. Now, remember we also spoke about steady state flow. We said for steady state flow, all we are saying is that at every location, the property or the value is constant. So what steady state flow is trying to say is that I can have a case like this. But every time I check the middle, it is 2 meters per second. There's not a point where it becomes 2.5 or 3.5. It is always 2. So that is where we have steady state flow. Okay. Okay. So that's where we have steady state flow. Is that okay? So um, so what we're saying for steady state flow is that at every point, at every instance, when we measure the frequency, it's not changing. Uniform is saying that at every point it is the same value. So uniform is saying that at every point it is 2, or at every point it is 3. Right? But then steady is saying that maybe at one point it can be 3, at one point it can be 2. But then at the point it is at, it is not going to change. So for steady, this is at 3, this is at 2. Every time I check the inlet, it is at 3. Every time I check the middle, it is at 2. Every time I check the outlet, it is at 1. So this is non-uniform. but it is steady. If I had a case where I had the same, and it was 1, 1, 1. Every time I check the inlet, it is 1. Every time I check the middle, every time I check the outlet, it is still steady, but this time it is uniform. Do we get the difference? Please, do we get the difference? Okay, sure. I'll take it again. This is what we are saying. So let's say we have two pipes, right? We have the inlet, we have the middle, we have the outlet. Now, for the first one, the velocity of what's coming in is 3 meters per second. It drops to 2 in the middle, and then it drops to 1 at the outlet, right? If we have a case where the values are changing along the pipe, then we have a non-uniform flow. So it's not uniform because I start with 3, I go to 2, and I end with 1. If it is uniform, at every point, it's the same. So when I check the inlet, it is 1. When I check the middle, it is 1. When I check the outlet, it is 1. Are we okay with the first part? Please, are we okay with this part? Okay. Now, what we are saying about steady is that realize that here, this is 3, this is 2, and this is 1. If I have a case where I look at just the middle, right, and I'm measuring the velocity at just the middle, every time I measure it, it is 2. It doesn't go to 2.5 and come back to 2. Then that's a steady state flow. If I was at a point where it was at 2, I measured it maybe in 10 seconds and then it moved to 2.5. I measured it again after 10 seconds and it moved back to 2. That is on steady state flow. Because at that point, it is changing. So what we can say for steady state flow is that we are considering what happens at a point. What happens at the point if it is changing? Okay, I'll answer the question. So what we are saying that if it is at a point, right, if you're considering what is happening at a point, just at a point, and at that point there is no change, then it is steady. If at that point there's a change, then it is unsteady. If you're considering the entire thing and there is no change, then it is uniform. If there's a change, it is non-uniform. So there's a question that's saying that please, it means uniform is also steady, but steady is not always uniform. Yes, that's exactly correct. So uniform flow, okay, uniform flow can become unsteady. It's a little bit complicated, but then for now, we just take it that uniform is steady. Or we can have cases where we have, if you're looking at maybe an entire system, not just one single part, we can have uniform and then still non-steady, right? But then for the sake of understanding, to make sure it doesn't get even more confusing, yes, uniform is steady, but steady is not always uniform. Is that okay? Okay, so this is what we are just saying. So once again, for uniform and non-uniform, we are considering the entire system, right? So if at every point it is the same value, then we have uniform. For non-uniform, it changes, right? But then for steady and non-steady, we consider each position. So if I'm at the middle, I'm looking at the middle. If it doesn't change in the middle, then it is steady. If it changes, it is unsteady. If I check the end, it doesn't change at the end, it is steady. If with time it changes at the end, then it is unsteady. Are we okay with this? I think this is the third time we are explaining steady and non-steady states. But then we just added the uniform and non-uniform to it. But I hope you get it. Okay. So now we can also consider physical properties to be extensive, intensive, or specific. We'll not take time here because we've spoken about it both in CPC and then in thermodynamics. So I think it's fine. We just said extensive properties will depend on the amount of the material we have. And that's extensive. Intensive are not dependent on the amount of material we have. And the specific properties are basically extensive properties that we are defining by mass to make it intensive, right? By mass or by moles. So we'll not take too much time there. And we can consider density as well. So density is a property of fluids, right? And we know the formula for density is just mass over volume. What we are saying is that density can change from point to point in a system that is not uniformly mixed, right? And it can also change with respect to time. So I can have a mixture, and then the density would be different at different points in that mixture because the mixture was not well mixed, or it wasn't a uniform mixture. Is that okay? And then we also know that we said density is mass over volume. So if we look at the change in mass and then the change in volume, and we take the limits as a change in volume is approaching a very small value, right? Then we can get what we are looking for, the density we are looking for. So this is just calculus, our first principle what was the name? For differentiation, right? Yes, the reason why we are using the delta V, the very small change in volume, is that we said that we want to look for the smallest volume, right, around the point for which statistical averages are meaningful. So that's where the continuum thing we talk about comes in. There's a certain volume that is small enough for us to do our analysis, right? So that's what we are just considering by the delta V. So when our change in volume is approaching that very small value, right, then we can analyze it and then get what we are looking for. That's the density. Now, we have fluids whose densities remain almost constant over a wide range of pressure and temperature. We call them incompressible. Okay, when we consider liquids, their densities depend very slightly on temperature and pressure. So usually we can ignore their variation. So we can check the density of water, and our values would always be very close to 1,000 kilogram per meter cube. So maybe I check the density of water at 25 degrees Celsius. It was 1,000 kilogram per meter cube. I take it to maybe 70 degrees Celsius, and then it just drops about 999 kilogram per meter cube. Like that, there's not a significant change in the density. So usually for liquids, we usually assume that they are incompressible, right? Unless it is stated that this liquid or this liquid is compressible, right? And then for liquids and gases, we can see that when their velocities are less than 30% of the speed of sound, and then the pressure doesn't vary greatly, then we can say that they are incompressible. So they came about this through some experimental work, right? And there's this thing, they call it the Mach number. So you can decide to read more on it. It's MACH, yeah, the Mach number. It just compares the velocity of the fluid to the velocity of the speed of sound in air. Right? And then if it is below 30%, we are saying that we can treat it as though it is incompressible. So they were considering maybe a plane moving in the atmosphere. As it's moving, there's air that is also moving on it. When the velocity of that air was less than 30% of the speed of sound, they realized that the density of the air didn't really change considerably. But then when the plane now moved faster, and then the air was also now having a higher velocity, right? They realized that when they measured the density, it kept changing. It wasn't incompressible anymore. Is that okay? That was one of the ways they looked at it. Now, when we continue with density, we are saying that for a gas, the density can vary significantly with both temperature and with pressure. So at low pressure, the density of the gases, we can approximate them very well using the universal gas law, right? Or ideal gas law. Because when we have very low pressures, we can assume that our gas is quite ideal. Is that okay? So we know our formula PV is equal to nRT. We can find the density from this. So we did this even when we're looking at sequencing and thermodynamics. I can change the number of moles here to mass over molar mass, divide the volume by the mass, then that will give me density. If I make that the subject, I'll get this, right? So T is our absolute temperature, M is our molecular weight, P is our pressure, R is our gas constant. Right? So we are very fine with this formula. We know that density is dependent on pressure and temperature for most gases, or for gases in general, yeah. Then we also have what we call specific weight and specific volume. Now, specific weight is given by this expression over here, right? So we have, if this is gamma, yeah, so we have gamma is equal to rho times g. We have our density times our acceleration due to gravity. Now, when we consider properties as being divided by moles or mass, that's when we said it was specific. But here's the case where we are having weight or a certain mass. We can't divide it by mass again. So in order to get something specific for weight or for mass, now we rather divide by volume. So this is what I'm trying to say. realize that if I have maybe what should I use? So let's say we have enthalpy, right? If I wanted to be specific, I can divide by the mass of what I'm dealing with. Now have my specific enthalpy. But here's a case where now I have mass, right? And then if I multiply it by the acceleration due to gravity or acceleration, I can get the weight. Now, if I want to make this specific, I can't divide it by mass again, because if I do, I'm just going to end up with acceleration. So when we are considering mass or weight, and we want to consider it as a specific property, this time rather divide it by a different value, which is volume, right? And realize that if I have mass over volume, that's giving me the density over here times the specific gravity. So with specific weight, it is just our weight divided by our volume. And when we look at specific volume, it is the inverse of density. So we know that density is mass over volume, right? So if I want specific volume, then it's going to be volume over mass. So to be the inverse of density or the reciprocal of density. So that's what we see down here. And specific volume is just V over M, which is 1 over our density. Yes, it makes it intensive. It makes it intensive. Now, we also spoke about specific gravity. And we said that is the ratio of the density of a substance to the density of water at some specific temperature. Usually we consider 4 degrees Celsius, right? And we say the standard specific gravity, measure it at 1 atm and then 4 degrees Celsius. So if the specific gravity of an oil is 0.98, it just means that the density of the oil compared to the density of water under these conditions is 0.98. We know the density of water under these conditions to be 1,000 kilograms per meter cube, right? So it means that for the oil, it has to be 980 kilograms per meter cube. So the 980 divided by the 1,000 give us a 0.98. To specific gravity, we just compare the density of the liquid to the density of water at 1 atm 4 degrees Celsius. If it is a gas, we compare to the density of air. Is that okay? Okay. Now this is where a lot of the discussion is going to come in. So we are now come to look at what we call viscosity. When we talk about real fluids, right, they resist any force that tends to cause one layer to move over another. Remember we said for fluids, you can consider them as layers moving over each other, right? So for real fluids, they are going to have these layers moving over each other, but then they are going to have this point where the force is going to be resisted. So remember we had with the animation we saw, there was a point where we had fluid flowing, and then we had an upper part with a higher velocity, a middle part, and then a lower part with a very slow velocity. What we're saying is that as the fluid is moving this way, there's one layer here, there's another layer here. The one on top is going to be introducing some kind of shear on the second layer. Right? But as it's doing that, there's going to be a resistance so that resistance is what we call viscosity. Is that okay? So the resistance to the movement of one layer of fluid over an adjacent one is the viscosity of the fluid. Is that okay? So it's like you realize that if you are walking, the soles of your shoes are one layer, the ground is another layer. And as you are walking, there's a resistance to your walking. That's where friction comes in. Right. Here's a case where now instead of your shoe on the ground, you have 2 layers of fluid. So there's still some resistance in there. And realize that when you're walking, we say we are calling it friction. For viscosity, it's not going to be the internal frictional resistance. So there's a certain kind of frictional resistance, but it is within the fluid. So we call it the internal frictional resistance to flow. So it is resisting flow, right? And we say that this is a measure of the fluid's ability to transmit shear stresses. So this part about transmitting shear stresses, we'll talk about it as we progress. So there's a graph we'll use to explain this, and that's where we'd understand the whole thing of momentum transport, where momentum is being transported. So for now, what we're saying is that if you are dealing with actual fluids, there's this tendency for the layers to cause resistance to adjacent layers as they are moving. Right? And this is what is called viscosity. And it is also a form of frictional resistance to the flow of the fluid. Because it is within the fluid, we call it the internal frictional resistance to flow. Now, let's consider a thin film of fluid confined between two large infinite parallel plates, the lower one being at rest and the upper one moving parallel to the bottom plate at a constant velocity. So we would visualize this very soon, right? But what we're saying is that I have one plate here, I have another plate here, and then there's a fluid in the middle of the. What we are doing is that we are keeping the one at the bottom constant. So the velocity of, or the force acting on that plate is zero, or the force coming from that plate is zero. And then we are going to move the one at the top with a constant velocity v. Right? So we have a fluid in between two plates, and we are moving the plate on the top. And now the distance between the plates is what we are going to call y. So there's a certain distance between the plates. The plates are y apart. Right? Now this is easy to get conceptually and mathematically, but we don't use this in real life because if you have fluid between two plates, definitely the fluid will leak out, right? Or the plates being on top, the plates resting on top of the fluid will be pulled down by gravity. So we don't actually measure viscosity this way. The other devices we use to measure viscosity, viscometers, rotothermers, there are different devices we use to actually measure viscosity. And this is just supposed to help you get the concept of what we're talking about, right? So we can also imagine the fluid as being subdivided into infinitesimally thin layers. So we think about the fact that we can consider the fluid to be made up of several layers, right? And they are saying that we can visualize this as thin layers that are parallel to the plates, like a deck of playing cards. So now if I have playing cards and I stack them onto each other, each card is representing a fluid layer. That's what we are just trying to see. Is that okay? So we can consider the fluid to be, sorry, I'll take my time. We can consider the fluid to be made up of different layers, right? So all we're just trying to say is that this particular model they are using, they don't actually use it to measure viscosity in real life. They're just using it to help you get the concept, right? And what we are saying is that we have two plates. We have a lower plate and we have an upper plate. The lower plate is not allowed to move. The upper plate is allowed to move. And the fluid in between, we can look at the fluid like a deck of cards. So the deck of cards, realize that if I stack them on each other, each card can represent a fluid layer, a layer of the fluid, right? So I have layers of fluid stacked on each other, right? Now, each liquid layer would move in the x direction. So this is the y direction, the distance between the plates. The x direction is in this way. So each layer is going to be moving in the x direction. So we'll see that very soon, right? And the layer below it is at a slightly lower velocity. Each layer moving at a slower velocity as we go down the y direction. So I'll show you that very soon. And then the layer adjacent to the stationary fluid will be at rest. So this is what we are seeing. I have two plates here, right? So we'll come to the animation soon, but then let's look at the graphs for now. We have two plates here. The lower one is stationary, it's not allowed to move. But the upper one is moving with a certain velocity, that is the V here, right? And there's a certain shear force acting on it, that's the Fs. Now these two arrows here are representing the layers of the fluid. What we are saying is that as the fluid is moving, because the one on top is moving, it is going to transmit force to the next layer. Then that layer is going to transmit force to the next layer, and it will keep transmitting force downwards till it gets to the base. When it gets to the base, most of the time, the fluid at the base usually doesn't move. So please take note of this. The liquid just above the lower plate is not going to move. We call that the no-slip boundary, where we consider the fact that the liquid is stuck to the surface, it is stationary, it's not going to move, it is fixed there, right? Okay. And then as we are going up, realize that the velocity is going to be increasing. When we're coming down, it was decreasing. So we had the plate at the top moving at its own velocity. It transferred some force to the next fluid layer. That one also transferred some force to the next fluid layer. And it continued to transfer. So the velocity dropped to zero. So this is the velocity profile. At the top, it is very high, but then it drops to zero over time. Over the distance, right? It drops to zero over the distance. This is where momentum transport is now coming in. Because remember, we said that for momentum, we're looking at a velocity gradient. We're looking at the transfer of the force through that velocity gradient. Right? So realize that as the plate is moving, it's transferred some amount of force to the next layer. When it transferred force to the next layer, that layer offers some kind of resistance. So it's not going to have the same velocity. It will have a lower velocity. And the next layer also offered resistance. So with the image or with the animation we see here, realize that if you look at the top, the fluid seems to be moving faster. But if you look at the bottom, the fluid seems to be moving really, really slowly. Do you see that? So the one that is moving at the top is going to move very fast and it's going to um, transfer its force to the next layer. But then because that next layer is going to offer some kind of resistance, it wouldn't move as fast as the one at the top. That's a question. Okay, I'll go over again. Let me finish this part. So we are saying that the one at the top is moving quite fast, right? And as it moves, so the one at the top is moving quite fast. As it moves, it's going to introduce some force to the layer just beneath it. But then that layer is also going to offer some kind of resistance. So that layer will not be able to move as fast as the one above it. And then that layer is also going to transfer force to another layer below it. So the layers would keep transferring force to the layers below it. And the ones below them will keep becoming slower and slower. So we see at the top here, the fluid is moving quite fast. And then at the bottom, it's moving quite slowly. And it generates what we call the velocity profile. So at the top, the velocity is quite high, or it's larger than when we come to the bottom. And when we just get to the surface of the plate, the velocity there approaches zero. So someone is asking that please, the surface of water could be still while the bottom is in motion. Yeah, you can have a case like that. It depends on the kind of system you have. So this is what is going to happen. But that's quite rare and difficult to get. Right. What we are looking at here is we have one plate down here, we have one at the top, and the one at the top is moving. If we had a case where the one at the top was rather stationary and the one at the bottom was rather moving, then what you are saying can come into play, right? That's if you want to picture something like that. But then in reality, we don't have that actually happening. Is that okay? And the one who wanted me to go over, is there any part you want me to take or you are fine so far? No, no, in reality, it wouldn't work that way. Is the one who wanted me to go over this, which parts would you want me to take? Or we can move on. Okay. Okay. She says she gets it now, and that's fine. Okay. So yes. So to still buttress what we were saying, right? So this was the first animation we looked at. So as the one at the top is moving, it would introduce some force to the one in the middle. Is that okay? That will also introduce some force to the next one. And we realize that as the force is being introduced, it's going to cause there's going to be some kind of resistive force between the layers. So the one in the middle is not going to move as fast as the one on top. The one at the bottom is not going to move as fast as the one in the middle, right? So we can see that velocity at the top is higher than velocity at the bottom. And because there's a velocity gradient now, we can see that momentum is being transferred from the top to the bottom. Is that okay? When we look at this one as well, we can look at the deck of cards. Then as he's introducing force to it, it's moving in this direction. So we can see that the top is moving more than the bottom. The bottom almost looks stationary. Do we see that? So that's what we are just trying to say by the mostly boundary. The bottom almost looks stationary. It's as though the bottom is not moving at all. But then we see the top moving. That's what happens with fluids. So as our fluids are moving, the part that is just on the solid surface, please note, the part that is just on the solid surface doesn't move. We call that the no-slip condition or the no-slip boundary. That region just above the solid part where there is no movement. The reason why I'm emphasizing solid part is because if we had a case where I had a pipe, right, realize that the top is solid, the bottom is solid, and they are not moving. So the two conditions, the solid, or there has to be a solid layer, and that solid is stationary, that solid is not moving. If I have a pipe, right, the top and the bottom are solid, and they are not going to move. So it means that there's a point at the top where the fluid is fixed there. There's a point at the bottom where the fluid is also fixed there. There's not going to be any movement of fluid there. You get it? So when we looked at the animation so far, the velocity profile was something like this, right? But in a case like this, it is going to be something like this. The reason is that at the solid points, there's not going to be any velocity. So the highest possible velocity would be in the middle. And then it reduces as you go up and reduces as you go down. Right? I think we see that as you progress. But what I want you to keep in mind is that when you have a solid surface that is not moving, you can have your no slip condition, or your no slip around you. So the fluid is attached to the surface and it's not going to move. Is that okay? Okay, now back to viscosity. The thing has a force, or in this case, a shear force. So as we are using the subscript S, it must be exerted on the upper plate to maintain the motion. Then an equal and opposite force must be exerted on the stationary plate. So it's convenient to use not the total shear force, but then the shear force per unit area of the plate called the shear stress. Right. So what we are just trying to say is that instead of us flexible, the force that we are using to move the plate, or the force at which the upper layer is going to move, we can look at the shear stress. So that's the force per area, and that is better for our calculations. Right. So this symbol here, tau, is what is representing the shear stress, and it has two subscripts or two indexes, as we can see. So the first index shows that the shear stress varies in the y direction. So realize that as we looked at the system, the velocity was decreasing in this direction. That means the amount of shear stress available was reducing, right? Because there was some kind of friction coming in. So it was reducing the amount of shear stress available. So it was reducing in the y direction. That's what the first index is showing. Then the second index shows the direction in which the shear force and shear stress are. So the shear force was acting in the x direction, parallel to the direction of the fluids. Because remember we said for shear forces, they are acting parallel or tangentially to the surface you are considering. So they are acting in the x direction because the fluid is also flowing in the x direction. So they are parallel to the direction of our fluid motion. This is that okay? So shear stress is just the shear force over the area, right? That the shear is happening, or that the shearing is happening. And then the first index here is just telling us the direction in which the shear stress is going to vary. And then the second is showing the direction in which it actually acts, or the direction in which it is moving. Is that okay? Oh, sorry, there was a question. I didn't see it. Someone asked that local fluid velocity on the graph. What does it mean? Okay. Okay, when we talk about local fluid velocity, right, or when we talk about any property and we include the word local, other things that we're just considering a certain region, right? So we are just considering it as a particular, do not over the entire system. Is that okay? So we've picked just a portion and we're looking at what happens at like that particular portion. Okay. Sorry, I missed the question. Now, I think we're talking about this, yes. So experiments indicate that the direct proportionality between the shear force and then the velocity and then the area of the plane, right? So they were able to derive this formula through experiments. And what I'm saying is that if we let y approach zero, then we can have it written in this form. So you know our Fs over As is our shear stress, that's the tau, right? Then we have the delta V delta Y. When Y is approaching zero, this is like our first principles with differentiation. When it is approaching zero, then we get dV dy. So this is the change in velocity, but then the velocity acting in the x direction. That's why it has a subscript of x. But the velocity was changing in the x direction. Is that okay? I mean, sorry, the velocity was moving in the x direction. All right, so that's what we are using there. So the shear stress is just equal to this expression, the change in velocity with respect to the change in distance. And I think we understand this, but talk about the fact that we need a velocity gradient. So this is our velocity gradient, right? And then the constant of proportionality is what becomes our viscosity. So we have here tau y, and that's the shear stress exerted in the x direction. Vx is the x component of the fluid velocity. And then mu is the dynamic viscosity. So that becomes our viscosity. And then this expression is what we call Newton's law of viscosity. This is now okay. Are we fine with that? That expression is what we call Newton's law of viscosity. Now, the units we use for viscosity, we can have it in pours. So if we say 1 pours, it is 1 gram, sorry, it is 1 gram per centimeter second, right? Or you can represent it with 0.1 Pascal second, right? So this is the units for viscosity. We can also have it in centipour. So we learned that if we say something is centi, that's 10 to the power minus 2, right? So I have 10 to the power minus 2, right? If I change the centi here, I can make it in the power minus 2 power. But we said 1 power was 0.1 Pascal second. So if I have 10 to the power minus 2 and I multiply by 0.1, I'm going to get 10 to the power minus 3. So that's where the 10 to the power minus 3 is coming from. Please then take very, very good note of these things. Because these units, if you are not careful, you can make a lot of mistakes later on in this course. Yeah, so please really take note of the units and then converting from power to Pascal second. Right? Okay. So the above empirical relation is known as Newton's law of viscosity. That's this relation here. And it states that the shear force per unit area, that's the Fs over As, is proportional to the negative of the local velocity gradient. So that's the dvx dy. And the proportionality constant is called the dynamic viscosity. So we've already spoken about that. The velocity gradient is often called the shear rate. So the shear stress is proportional to the shear rate. So instead of calling it the velocity gradient all the time, we can also call it the shear rate. Is that okay? Is that okay? I want someone to try and answer this question. Why is there a negative here? Why do we think there's a negative here? I want someone to try. Why do we think there's a negative there? Or I should mention names. Anyone? Why do we think there's a negative here? What do we think? Okay, let me make it a little bit more understandable. When we're talking about, I think there's an answer. Okay, good. So that's the answer. So the velocity will decrease with time down the fluid, right? So when we're looking at mass, look at high concentration to lower concentration, we're moving from a higher to a lower concentration. So that change, that gradient is a downward slope, it's negative. Right? Same thing with heat, higher temperature to lower temperature. Velocity to higher velocity to lower velocity. So it's because the velocity is decreasing with time down the fluid. Amanda, thank you very much. Okay, so, okay, talking about this. Fluids that obey this equation, for we've spoken about the equation, right? They are called Newtonian fluids. So the viscous shear stress in the fluid is primarily a result of the intermolecular forces. Right? So the amount of shear stress we can get from a fluid is highly dependent on the kind of intermolecular forces between the molecules. In examples of Newtonian fluids, we have all gases, all liquids for which the simple chemical formula can be written, like water, ethyl alcohol, hexene, right? And their molecular mass is less than 5,000. Then we are also saying that most dilute solutions of simple molecules in water or organic solvents. So you can read this later on. These are just examples of fluids we call Newtonian. It's fluids that obey this relation. So there are some fluids that deviate slightly from this relation. So we'll talk about them as well. I don't know if we'll talk about them today. I will talk about them. So the variation of the fluid viscosity with temperature and pressure is quite complicated. And usually we determine it experimentally, right? So when we want to determine the effects of temperature and pressure on the viscosity of a fluid, one of the best things to do is to do it experimentally, right? Because there are different fluids that behave differently, even though they might look similar. Right? But then on a general scale or from a general perspective, we can see that the viscosity of a gas would increase with increasing temperature, right? And then the viscosity of a liquid would decrease with increasing temperature. So I'll talk about why one is increase and one is decrease. Then the viscosity of an ideal gas is independent of pressure. And then the viscosities of real gases and liquids usually would increase with pressure. Right. So let me start with the first one. The viscosity of gas would increase with increasing temperature. When we are dealing with gases, right, usually the viscosity is highly dependent on the number of collisions that we are going to get. So if we have an increase in temperature, we have an increase in the collisions, right? And that's going to cause an increase in the viscosity of the gas. When we are dealing with the liquids, however, right, realize that when you increase the temperature, you are now going to cause the molecules to move more apart from each other. Initially, the molecules were closer to each other. So for liquids, it is how close the molecules are to each other that is going to inform how viscous it's going to be. If we increase the temperature, we are moving the molecules further away from each other. Right, so the viscosity will now decrease. So imagine you have a very thick liquid and then you heat it, right? That now becomes less viscous. Right? When we are dealing with ideal gases, we usually consider the fact that the pressure that is going to act on it is going to have a very small effect. Right? So we know for ideal gases, the pressure is very low. The moment the pressure becomes high, we are no longer dealing with an ideal gas. So as long as the pressure is sufficiently low, it's not going to be significant enough to push the molecules together or to cause collisions to happen enough for us to have viscosity increasing. Right? So for ideal gases, usually take it that they are independent of pressure. And then when we deal with real gases and with real liquids, and we increase pressure, we are pushing the molecules closer together so we can increase the viscosity. But once again, please take note that these are general cases. There are some cases where you would have a liquid and then you might be increasing the temperature and it's rather doing the other thing. Is that okay? So this is just a general case. But then if you have a particular liquid and you want to determine the effect of temperature and pressure on that fluid, usually we go experimentally. Okay. Now, another interpretation of the shear stress, right, is we can interpret it as the flux of X momentum in the y direction, which is the rate of flow of momentum per unit area. Now, the reason why we are saying this is because remember that momentum, if you're looking at the formula for momentum, we can look at it as mass times velocity, right? Or if I remember well, it is the same as yes, it is force divided by time, right? Now, remember we said if we have the different layers of the fluid, the one at the top is going to exert a force on the one below, but then the one below is going to offer some kind of resistance, right? So let's say the one on top is moving at 50 Newton. The one below will move at 48. Then the next one will move at 46. And it will keep decreasing until it gets to 0. Right? In that case, because now the force is reducing along it, we can look at it as momentum moving down in the system. There's momentum from the upper one, but it is transferring its force to the next layer, and then to the next layer, and then to the next layer. It's not transferring all of the force, but it's transferring a significant amount of the force to the next layer. So momentum is moving down. Right? So there's momentum that was moving in the X direction, but then its effect, you can see the change in the Y direction. So that's the flux in the Y direction. Is that okay? And we are saying that Fs, that's the shear force, is required to maintain the motion. So we need to have that force there to keep the motion. And Fs is acting parallel to the plane of the shear. I've already spoken about it. Shear forces would have to act parallel to the plane they are working with, right? And Fs is exerted by the fluid outside of plane C, on the fluid between plane C and the wall. So what we are just saying is that Fs is the force acting on this upper layer, right? Or the force from this upper layer, and it's acting on the fluid in this region, right? The fluid in this region. So that's the fluid between this plane and then this one. That's the fluid in that region. That's what we are just trying to see. And the moving fluid just above the plane C has slightly more momentum in the X direction, and the fluid just below it. So we are just saying that if we consider one plane of fluid or one layer of fluid, it has more momentum than the fluid just below, right? Because the force for the one just below is going to be smaller, and then the velocity is also going to be reduced. Right? And if momentum depends on force, it depends on velocity, and it is reducing as you go down, then it means that the one below would have a lower momentum than the one above, right? The random motions of the molecules in the faster moving layer send some of the molecules into the slower moving layer, where they collide with the slower moving molecules and tend to speed them up or increase their momentum in the x direction. So this is what we are saying. If we had a case where momentum was not being transferred, then when the upper layer is moving, I think I'm going fast. If we have a case where momentum is not being transferred, then when the upper layer moves, right, the next layer is going to be stationary. What we are saying is that when the upper layer moves, it's moving with a certain velocity. So it's going to have its molecules colliding with the molecules in the next layer and then introduce some force and velocity to those layers as well, right? So with mass, we looked at higher concentration to lower concentration. With heat, we looked at higher temperature to lower temperature. With moments, we're looking at higher velocity to lower velocity. Are we okay? Okay. So molecules in the slower layer, they tend to retard those in the faster layer. So the same way the molecules in the faster layer would speed up the molecules in the lower layer, the molecules in the lower layer would also slow down the molecules in the upper layers, which are moving faster, right? So this exchange of molecules between layers produces a transport of flux of momentum that was moving in the x direction, right? And it transports it from the higher velocity region to the slower velocity region. So we've already spoken about that. So there's a movement from the higher velocity regions to the lower velocity regions. That's where the momentum transfer comes in. So we can see that the x direction momentum is transported in the negative y direction because it's moving downwards, right? But the momentum tends to go in the direction of decreasing velocity. Momentum moves in the direction of decreasing velocity. Are we okay with that? So we can get a velocity gradient that would now represent our driving force for the transport of momentum. This is that fine. So we already spoke about the velocity gradient. There has to be a velocity gradient. That's going to give us our driving force. That's what's going to allow momentum to be transferred downwards. Okay. Hello. Okay. So this is the last thing we'll do for today. So we have kinematic viscosity. We've already looked at dynamic viscosity. When we talk about kinematic viscosity, what we are saying is that it is just the dynamic viscosity divided by density. And so sometimes we want to work with this term instead. Or if I'm given a question that will tell you that the kinematic viscosity is this. And so you divide it by, oh, so there's a question. Okay, I'll address the question. But all we're saying about the kinematic and dynamic viscosity is that if I divide dynamic viscosity with density, it gives me the kinematic viscosity. And please pay very good attention to the units because sometimes you'll be given a question and they won't tell you which one it is. But then if you check from the units, you realize that what I'm dealing with is dynamic, what I'm dealing with is kinematic. Do I have to multiply by density? Do I have to divide by density? That kind of thing, so that you know what you are working with, right? And there was a question that was asked. That was quite some time ago. Amanda, can you please ask again? You said that the velocity decreases with time down the field. Please, which parts? Let me see the question again. If you were answering my question. Okay, and that's fine. Okay. You were answering the question about why it was negative. Yeah, okay. So that will be it for today. That will be it for today. We'll continue tomorrow and we'll look at the different kinds of fluids we have. Is that okay? Let me see if I have the attendance link. So I think we can end the recording now. But are there any questions? While I try to get the link, if you have any questions, you can ask. Okay, so the link hasn't been sent to me. So what we'll do is that I'll just take note of all those who joined the meeting, right? Or those who joined at least up to this point. I think I have some of your contacts. So those whose contacts I don't have, you can text me. I'm just taking note of all the people who joined today. I mean, those who at least joined up to this point. So those who don't have my number, you text me. As soon as I get the link, I'll send it to you. Okay. So that's my contact. Um, so you text me, I'll send it to you when I get it. I'm sure you'll send it to me by this evening. So I've taken note of every so join. Okay, so we'll continue tomorrow, God willing. I'll send you the original material, Miss Mumaday's slides, and then I would send you the links as well to the YouTube video so you can get more information on the things we are talking about. Okay, so if there are no other questions, I think we can end this for today and I will continue tomorrow. Okay, so that's my contact. Then you can just text me on WhatsApp and I'll send you the link when I get it by this evening. Okay, so thank you all for your time.